Okay. Oh, I forgot to unfreeze.
Yeah.
So far, we have been taking the derivative when there's just one variable, right? Usually it's x, sometimes it's theta, right? And we've only been doing derivatives of functions. Okay, but what if we have a circle? Is that a function? No, because it doesn't pass
The line test.
the vertical line test. Okay, but does it have a derivative? Okay, has a derivative everywhere. Can you find the slope? Like, can I find the slope there?
Yeah.
It's 0, right? Can I find the slope here? Yeah.
Yes.
But what happens here and here?
It doesn't exist.
Okay, so that's an undefined slope, so it won't have a derivative there, but it has a derivative everywhere else. So what we want to do is we want to figure out how can we find the derivative. Well, some people might think, well, could I solve for y and then take the derivative? You could, but then you'd have to do the positive and the negative, right? And what we want to be able to do is we want to be able to take the derivative all at once and then be able to find it at any one point. Good? So we see the goal. Now we have to see the process. Implicit differentiation is really just fancy chain rule. So that's why we do chain rule before we do implicit differentiation. I will explain, or attempt to. Okay. Here's what we want to do. We want to find dy dx of that function x squared plus y squared equals 9, right? Circle with radius 3. So I want to take d dx of both sides. Just like solving equations, we have to balance our equation. So whatever we do to one side of the equation, we have to do to the other. Okay. Good so far? Didn't really do anything. We just put a d dx on both sides. Okay, now what I want to do is I want to take the derivative of each part. So I'll try to, I should have given you a little more space here. Sorry about that. Can you see now? Okay. Sorry, we'll have to continue down here just for space. It's fine. Okay. Whenever we're taking the derivative with respect to x of something in terms of x, we just do the derivative like normal. So what's the derivative of x squared? 2x. Perfect. Now, technically, it would be 2x dx dx, which dx dx is 1. I'll explain. When we get to the next part, the derivative of y squared. So what we do is we treat y as a differentiable function in terms of x. Okay, what that means is we're going to do the derivative like normal. So derivative of y squared is 2y. We treat y like the inside part for chain rule. So what's the derivative of y? dy dx. So it's kind of like, remember when we had the inside? We treat y like the inside. So if I'm trying to find the derivative of y squared with respect to x, right? We would say move the 2 to the front, y to the first, times the derivative of y. So times y prime, or in this case, I'm going to just write it out as dy dx. Okay? No, you're shaking your head.
You can write y prime.
You can write y prime. That's fine. I get in that when we get to something called related rates, which has to do with d dt of both sides, then you have to write it this way. If you want to write, I'll show you on the next page. We'll do some more examples where we'll just use y prime if that's easier. Okay?
Why would we do that with x then?
Well, technically you do. So it would be dx dx. But what's dx dx? 1.
Oh, that makes sense.
If I did the derivative of w squared, it would be 2w dw dx. Okay, so anytime the variables don't match, we have to multiply by the derivative of the inside, which is the derivative of that, right, that variable. Okay, Misha, and then.
How do you know that the variables don't match?
Well, look, how did I write it? What did I write to begin with?
dx.
I'm trying to find d dx of both sides.
How do you know?
Well, x and y don't match.
How do you know that you're finding dx? Like, does it?
No. Okay, so that's.
Is that just always what you're trying to find?
Yes.
Okay.
Okay, what's the derivative of 9?
0.
0, good. Okay, now, what do I want to do? I want to solve for dy dx in terms of x and y together. Okay, so I'm going to subtract 2x from both sides, so I'll have 2y dy dx equals negative 2x. Divide both sides by 2y. So dy dx equals negative x over y.
Yeah.
Okay. That means, going back to the circle, if I have an ordered pair on the circle, I can find, right, I can find the slope of a circle, and it's always going to be defined as negative x over y, so I need to have the x and the y coordinate. Before, when we did this, we just had the x to plug in, right?
So we can like remember that and use that for any circle? Or should we still be expecting?
Yeah, I mean, yeah.
Like, could we like know like there's the derivative for any point?
Any point that's anytime it's centered about the origin. That will
always
that'll be the case for any circle.
If it's like shifted
Yeah.
over, it wouldn't.
It's going to be well, because your ordered pairs are, yeah.
Okay.
So I have another example too. So you could see example 2 is a circle. So already we know we should get the same answer.
Okay.
Okay.
So when you plug in, like, so if you plug in any x value into x over y, whatever you get is the slope at that point.
Mm-hmm.
Okay. What? So, like, at that.
Well, okay. Let's say I said, I'll just do a quick example. What if I said when x equals 1 and I didn't give you a y value? Well, I have that function that I can plug into, right? So 1 squared plus y squared equals 9. So y would be equal to, so y squared would be 8 square root. So it would be plus or minus 2 root 2, which makes sense because when x equals 1, don't I have 2 places where I have? So and obviously so 1, I would look at plugging in 1, 2 root 2, and the other point of tangency would be 1 negative root 2 over 2, and then you would plug those coordinates into the negative x over y. Okay? That makes sense? You can kind of see it visually, how if we plug it in here, it makes sense that this would be a negative slope, and then here you would have a negative over negative, so that would make it a positive slope. Okay, good. So let's try y squared equals x. What's that graph look like? Sideways parabola. You can also think of it as plus or minus the square root of x. So we know what the square root function looks like. Just a quick sketch we don't need to do. Right? Okay, and what am I trying to find? I want to find the slope at 4, 2 and 4, negative 2. Okay, so I'm going to take d dx of both sides of my equation. Okay, so again, we treat y like an inside function. So we're going to move the 2 to the front times y times the derivative of the inside. So that's going to be my dy dx. And now what's d dx of x? Just 1. Question, Ryan?
I was going to ask, But they like switch out like the y value for something else. Like in different problems, I remember you said earlier that like you could have like d dx, but like the y value could be like a dumb word. I think that's what you said, right?
It can be any variable. We still treat it the same way. Okay, what's the derivative? It's going to be 1 over 2y. So now we want to find dy dx at the point 4, 2. And we'll do dy dx evaluated at 4, negative 2. Notice this time, there's no x to plug into. So that means your slope for this function is based solely on your y coordinate, okay? What do we get for the 4, 2? So like here. It's not, it's just 1 over 2 times y. 1/4. Yeah, don't be shy. Don't be shy. Come on. It's not. And then negative a fourth. Oh, that was a bad tangent line, but there we go. Questions? Yeah.
So what would you do if like the y had a coefficient? Like, cause what did it?
That's fine. So let's say if it was 2y squared,
Yeah.
then it would become 4y dy dx.
And then when you're doing the dy, it wouldn't be like d2y dx, right? No.
Wait, say that again?
Like, let's just say, yeah, so it was 2y squared. Then, also you just take the coefficient out, and then.
Yeah.
Because I was just saying, like, it would still be dy.
Yes. Let's actually, I'm going to skip example 2 because it's just like this one that we already did. So, yeah, let's do that with this one. Let's do example 3 with a y prime to see if that makes, I know it gets a little tedious writing that dy dx all the time. I'm okay if you just write y prime for now, but in a later section, we're going to have to write the whole thing out. That's all I just wanted to get you used to both ones.
I just want to see how it looks with
I'll-
the y prime, 'cause it's
I'll
not
do
as
that.
confusing.
Yeah. Andrew and then Ryan.
Really quickly, if you just go up,
Uh-huh.
if it was y cubed instead of y squared, so it was like
Okay, if it's y cubed, it would be 3y squared
and then
times dy dx. Because remember, the inside is still your y.
So regardless, it's just gonna dy dx is never gonna be squared or cubed. Right?
No.
It's
So
gonna be dx.
your dy dx is really just your chain rule. It's like saying y is our inside function.
Oh.
So we do the derivative, but then we have to multiply by the derivative of the inside. But the inside is
always inside, no matter if there's a
Yeah.
coefficient or an extra, like.
exactly. So let's look at this next one where we have some different things going on. Okay. All right, I'm writing d dx to start because I in every case that's what I'm doing. I'm taking the derivative of, I won't always show the steps. Eventually I'll just jump right to it, but for now I'm just trying to get you to see. Also not to forget whatever you do to one side you have to do to the other. Okay, what's the derivative of 2y? Okay, so that's just going to be 2 dy dx. And then this time I'm just going to write 2y prime. So you can kind of see what that looks like. Good? All right, what's the derivative of x squared? 2x.
Oh, and then you don't have to put dx.
I don't have to write dx dx because that's just 1. Okay. Plus, all right, now, this is where it gets a little, because now it's not just something in like y squared. Now it's sine of y. So what do you think we're going to have to do here? Chain rule. But it's fine. This is fine. Don't. What's the derivative of sine? Cosine of y times, what's the derivative of the inside? Y prime.
Wait, so can you still, so that you can still write dy
Okay, remember, derivative of the outside, keep the inside the same, times derivative of the inside.
And y is always like its own inside.
Y is always the inside. It's like its own inside. So anytime
There's
you
like a y
take the
inside the y.
there's a y inside the y. So anytime you encounter a y, you're going to do the derivative just like normal, but then you're going to multiply by y prime because that's really performing that chain rule. Okay,
So
Um,
if it was sine of x, it would just be cosine.
yeah.
Oh, okay.
If it, so Molly just asked, if this was sine of x, then you would just have cosine of x, right? But because it was sine of y, we needed cosine of y times y prime.
It's like
Oh, so it's like the chain rule. The chain rule only applies to sine y, not
Yes.
That's it.
Yes.
It's not the x
Exactly.
plus sine y. Okay.
Okay. All right. What do I have in this case? I have y prime on both sides. So what I want to do is let's move all the y primes to one side. So I'll have 2y prime minus cosine of y times y prime equals 2x. Why do I need to do that? Because I need to factor out that y prime, right? I'm trying to isolate the y prime. So I factor out y prime, we get 2 minus cosine y equals 2x. Right, we're going to divide both sides. Okay, so y prime is going to be 2x over 2 minus cosine y.
Because you need to get the derivative
That's the answer?
because it's the slope.
You need to get the derivative because that's the
Got
slope.
it.
That's the answer?
Well, we just found the derivative. We actually didn't answer the question.
No, we just found the derivative.
Oh, we just found the derivative. Oh, but addressing the question is straightforward.
Yeah.
What's it say? Show that the slope dy dx, or in this case we wrote y prime, same thing, is defined at every point on the graph. So remember this one where we had this, and we said the derivative was negative x over y? It's not defined for values when y equals 0, right? Because we can't have 0 in the denominator. But this one, we're saying this is defined everywhere. Why? Right. So 2 minus cosine of y will never be equal to 0 because the range for cosine is negative 1 to 1, right? So the range is always... So it's impossible to get the denominator equal to 0. So therefore, it's defined at every point. Okay? Yeah.
I still don't understand like if it was sine x, how like it was just sine x. Like when
No. If it was sine x, it would just be, the derivative would just be cosine x.
yeah, I don't like how come for y. it's-
Because you're differentiating with a different variable. Let's try a few more, and you'll see a pattern. You'll see a pattern. Okay, one more question, then I really need to move on.
So, wait, oh, no, Misha.
Misha.
Would you ever give us one with 3 different variables like x, y, and z, or are we only
Yes.
doing x, y?
Oh, that's really reassuring.
So you would still do the same thing?
Yep.
Okay.
That's what I was talking about in what our unit, our lesson on what's called related rates.
So that's 3.
Yeah, that can have 3. It can have as many variables as needed. Generally, the maximum is 3.
Okay.
You won't see on the
But
A/B
it doesn't
test.
like really like change anything? if it's-
No, it doesn't change anything. You'll see.
Then what would you solve for?
Okay, so the first one is x squared. So that's going to become 2x. Okay, now here, I'm going to put the subtraction sign out in front. I'm going to put like a bracket here so we can kind of follow. Because this is really x times y. So that's going to have to be a product rule. Okay. We got this. I'm not going to deal with the minus sign. Remember, I treat that minus sign just like if I had a coefficient, I would pull that out and I'll deal with it later. Okay, let's do derivative of x.
Wouldn't it be 1
1
times
times y. Okay, so it's u prime times v. Our v is just y. So plus x times y prime. Good. Right? So
Wait,
it's
why isn't it?
keep this the same times the derivative of y.
Oh, because the derivative of y is 1 and then you multiply.
Okay? Equals, what's the derivative of 7? That's a constant, so...
What's the y squared?
Oh, sorry, I missed that. Thank you. Okay. I think we got the y squared now, right? 2y times y prime? 0. Okay. The tricky part here was the part that I wrote in red because we had to do the product rule there, right? Derivative of x is 1, keep y the same, plus keep x the same times the derivative of y, which is y prime. Yeah, Abby?
How come you use the chain rule, not just the power rule for 2y?
Because it was y. We,
So it can't just be 2y.
did I forget to distribute my minus? Yes. Okay. So same thing, right? I want to get my y, since I have multiple y primes, I'm going to try to isolate those and move everything to the other side. Does it matter which way? Like, it really doesn't make any difference, however you want to. Maybe what I'll do is I'll leave the 2x minus y, and I'll move the xy prime minus the 2y prime to the right. Good. What was that, Ryan? Are we okay? Good.
Oh, we just took it out.
I just factored it out. So when you have a y prime in multiple places, it could be 2 terms, it might be 3 terms. It all depends on how many. Notice how many places did I see y in my equation? Twice. That means I should have 2 y primes after I do the derivative. If you only have 1, you know you made a mistake somewhere. If I had y 3 different places, I would have 3 y primes. Okay, so you look at how many times that variable occurs, and that's how many y primes or whatever we're looking at should occur. If you don't, then go back and check that. Does that make sense? Okay, all right, now we're going to divide. So what do we get? 2x minus y over x minus 2y. That's our y prime. And we want to evaluate that. Actually, we're finding the tangent. Don't worry about the normal. Same for your homework. Just a quick reminder, if you encounter a normal, you can ignore that. Just do the tangent. Okay, so what's y prime evaluated at negative 1, 2? What do we have? Negative 2 minus 2, so negative 4 over negative 1 minus 4, so negative 5. Yeah, so 4/5. Yeah, is that what you guys got? 4/5? Okay, and now let's just write the tangent. What's our tangent line? Y minus 2 equals 4/5 x plus 1. Okay.
You plug the negative 1, 2 into the y prime equation, right?
I did. Okay. Are we ready? Oh, now there's a second derivative. What fun. Okay. Of course there is. It only gets better. Oh man, and there's a lot of space on this page. Interesting. Scotty, I am going to have to talk to you after class. Do I have to call your mommy? Okay. Okay, how many y's do I have in my equation? 2. So once I do that derivative, I should have how many derivatives? 2. Good.
Oh, it's not about that.
It's not about the x anymore. It's all of the exponent?
Like, what is y?
Oh yeah, I still have to take in consideration. What's the derivative of y squared? It's going to be 2y, y prime. What's the derivative of 2y? 2y prime.
Oh,
Nice, huh?
We're taking the first derivative right now. and then the second derivative.
Okay. All right, I'm going to factor out my y prime.
I think we're gonna probably do it.
Good. And then let's simplify it while we divide. So it's really just going to be 1 over y plus 1. Excellent. Okay, so this is my first derivative, dy dx. Now, what I want to do is I want to take the derivative of that. Okay, so I'm basically saying, here, I'll do it over here. I want to take d dx of dy dx, and I want to take d dx of, hope it's okay, I'm going to rewrite that as y plus 1 to the negative 1. So I don't want to have to use quotient rule for something like this. I prefer to just use the power rule. Okay. All right, here, this is just the second derivative. This is how we express it. I think we talked about that previously. So we have the second derivative of y with respect to x. Okay. How many places do I see y?
1.
So I should have how many derivatives? 1. Okay. Derivatives of y, that is. What do we have? Negative 1. Keep the inside the same. Y plus 1. Take 1 away. Negative 2. Times the derivative of the inside. Y prime. Y prime. What if you want to put y prime or you want to write dy dx, it's the same thing. Okay. Just keep in mind there will be a time where you have to use the dy dx version when we have more than 2 variables that we're working with, or
Are we gonna get somewhere
The
with
inside,
Ah.
it wouldn't be y prime, prime.
wait,
Do you get what I'm saying?
there's only one y prime though.
No, I'm not saying that's not what I'm asking.
Wait, I'm sorry, what were you asking?
Like when you take the derivative of the inside, because you're taking like 2 derivatives of it.
But no, treat y plus 1 as the inside now,
Yeah.
right?
Yeah, I understand that. I was wondering because aren't we taking like the second derivative? Or not yet?
No, this is the second
There's
derivative.
only one y in this one, though, right? There's only one y prime in this one.
There's only one y prime. Okay, now I'm not done. Okay. We're not done because what was dy dx originally equal to? 1 over y plus 1. So that means my second derivative is going to be negative 1 over y plus 1 to the third. Now we're done. I guess I could have gone underneath here. I wanted to show here and here, so it's all on one part of the page. Yes, Ryan?
Are we gonna learn this lesson how to do it with multiple, like more than 2, or no? Is it this?
This lesson only has 2,
Oh, okay, then it wasn't 2.
but it will occur later where you'll have more than 2 variables. Mia?
No, it wasn't. I was asking if this lesson
Y
Mm-hmm.
would just be 1, right? So then when you're plugging
1 y prime, or 1 dy dx.
Yeah.
Yeah.
So then you multiply it at the end by like the first derivative.
Yes. Okay. I think this is last page. Okay. This is actually review from the chain rules. So we kind of already did these problems, but I already told you that the power rule works for any real number, and we've done this with rational exponents. So this is just more practice with it. So this is nothing new. Okay? Just a little bit of review from the previous lesson. Okay, how do we find dy dx? Is there any chain rule involved? Nope, not at all. This is just power rule. So what do we do? Negative 2x to the negative 3 halves. Right? So negative 2 over x to the 3 halves. Good? Yeah.
When you do it,
Uh-huh.
can we do it as the square root of x cubed?
Oh, yeah, absolutely. Because when we actually evaluate these, I want you to think of it in terms of the square root of x and then cube it. Okay, this one, let me just rewrite it as x times x cubed plus 1 to the half power. Now, what do we need here? We're going to need a product rule with a chain rule in it. Good? Do you want to try it or? Yeah.
Is the x considered a coefficient, so we just leave it as a side, or do we have to find the derivative?
You have to find the derivative of that. So derivative of x would just be 1.
Oh, because that's.
Wait, can we go over the steps again for that? Like, the 1/2 is the first step, right?
Okay, so treat the x as u and the x cubed plus 1 to the 1/2 as v. So u prime, so that's going to be 1 times, because there's a product rule.
Is it 1 times?
She's just making the product instead of
Okay, and when we do the chain rule, there's really just 2 parts to it. Because,
Why's that tripping me up?
right? Are we okay with this one? This one is just 1 times, keep the second one the same. Okay, now we keep x the same. Now, how many parts do we have to v? I have a 1/2 power, and then I have an x cubed plus 1 inside. So I have 2 parts. So I'm going to move the 1/2 to the front, keep the inside the same,
And then
subtract 1 from the power, so negative 1/2, times, what's the derivative of x cubed plus 1? 3x squared.
Oh. That makes sense now.
Okay. Now, this is not considered simplified form. This is also going to be one that we're going to factor out something. I guess let me just rewrite it real fast. X cubed plus 1 to the 1/2, and then that will be plus 3/2 x cubed, and then x cubed plus 1 to the negative 1/2. So when we're looking at these 2 terms, I'm going to take out the smaller one. I'm going to take out the one with the negative 1/2. So I'm going to take out x cubed plus 1 to the negative 1/2. I probably gave that's too much room. Okay, what do we get when we factor out?
to the
X cubed plus 1 plus 3/2 x cubed. Yeah? Okay.
I guess that makes sense. And then you put the x
We're-
cubed by the x.
This still isn't quite simplified. What would it?
Oh, you put
So-
you put it on. Can you put it back?
Yeah, you can also add.
You can combine the 3/2 x cubed.
Yeah.
Oh, you can?
Yeah, because they're like terms.
What's that? Yeah, you can combine those. So what's that?
5 times x.
So my final.
Is it fine if we leave it as like just the negative 1/2 instead of making it? Or do you prefer leave it? It's okay if you.
I mean, this is the best
that's the
form
best.
of that
Okay.
because you don't want to have a complex fraction. You don't want to have
Uh-huh.
fraction within a
Wait,
fraction.
isn't it plus 1 not plus 2?
Yeah, wait.
Yeah, I know, but if I have
Because
okay,
it's 5.
it's 5/2 x cubed plus 1.
Oh,
So I don't want to. So if I have 5/2 x cubed plus 1,
It needs to be 2 over 2.
then then you multiply by 2 over 2.
Oh, yeah.
Yeah.
Bro, but 3/2
Because I don't want you to leave complex fractions.
x cubed. She did 2 x cubed.
Oh, like
Plus
just
3 over 2. Like 5 over x cubed.
Okay, everyone. Calm down. I did not perform any math magic. I literally multiplied the numerator by 2, and I literally multiplied by 1. I multiply by 1.
I just don't get how you get the 5 halves. Like, how do you get that?
It's just adding